frames homework due on Sunday. Anytime a coordinate axis is given, note that your signs on your answers are based on positive X to the right and positive Y up. And so just a note there on the signs. And then also on this one, it asks for a dx and a dy, but BD is a two-force member. So find the force in BD and then break it up into an X and Y rather than trying to solve it as X and Y. Treat BD as a two-force member, which is what it should be treated as there. Okay, so we were working on this class example, continuing from last time. We are a little bit behind. We should be starting machines today, but it's really okay because frames and machines is exactly the same thing. In fact, the learning objectives are exactly the same thing. And you'll actually see a problem that looks like this on your machines homework. And also you'll see problems like this on your frames homework. So we had started and we had wrote down our given information here. So we have this member here that goes.
Yeah, it'll be a bit of a miracle if we get them to stay with us.
Okay. I think your dad
Who's okay? There we go. Okay. Okay. So we have member ABC up here. This one right here. That's a solid rigid object, and then this one right here is a solid rigid object, and then we have a couple of these pulleys. And we had drawn our given information and we're asked to find the forces at C on member A, B, C, and C to D. No problem about that, Colin. So actually what I want to do now is I made a demo of this last semester and a little video where we can dissect this. Let's dissect this example that we're working on in class. This example has a frictionless pulley here. It's got a frictionless pulley here and a rope that goes over each of those frictionless pulleys. And then we have a mass that's suspended from that frictionless pulley right there. Well, first, let's look at what's going on at those frictionless pulleys and how they transfer forces onto the rigid objects. If I take this frictionless pulley off right here, and we know that since these are frictionless pulleys, the tension in this rope is all the same. This is 0.5 kilograms. In our example, it's 50 kilograms. So we have 0.5 kilograms, and so we can convert that into a force by multiplying by gravity, and that would be the force that's along this whole cable here. And so we know we have, in each segment of that cable, we have that 0.5 times 9.81. Well, if I pull off this pulley here, and that's what we do when we draw free body diagrams, we separate things out. If I pull that off, what do you think I'm feeling right there? I feel a force trying to pull me this way, and I feel a force trying to pull me down. So that is the forces. Those are the forces that we're going to feel at that location, right? At this location right there. And in our FBD, we're going to draw a force going this way, and we're going to draw a force going this way, which is the same as the tension going this way and a tension going that way in that cable right there. Now, what about at this pulley over here? If I pull this pulley off of here, what am I going to feel in my hand right here? Well, I feel a force pulling it down, and I feel a force trying to pull back this way. And so we're transferring those forces from the pulley onto our rigid object there. Now let's think about drawing our free body diagrams. I'm going to remove the weight there just so I can pull things apart here, take off all my pulleys. So right here at this pin, we talked about we're going to have a force going this way from the pulley. We're going to have a force going this way from the pulley as well. But don't we also have the force, if we draw an FBD of this top object right here, we also have the force from this, oh, I'm falling apart here. We also have the force from this rigid object acting on that rigid object, and actually that's holding it up. So we're going to actually have two things in the X direction, two things in the Y direction happening there. Right here, we're going to have one thing in the X direction, one thing in the Y direction, the forces from those pulleys. And then we can also start to think about our options for free body diagrams. We could do a free body diagram of the whole thing, in which case I would just pull out the pin here. I would pull out the pin up here, and we could draw, but leave everything intact over here if we draw an FBD of the whole thing. Or we can start to separate these, and I can say, well, let's do an FBD of just this top rigid object, and we pull out the pin here and take everything off and show all of our applied forces. We could do an FBD of just this rigid object right here. And so we have 3 different possible free body diagrams that we can do for this problem. Okay, I'm going to go ahead and stop it right there. So we looked at the 3 possible FBDs that we could do for this particular problem. And the cool thing about statics is these are real problems, right? Like we can build the actual system there and we can see how it's behaving. You know, if we could get some system to be able to measure those forces, that would be, you know, really cool. Then we could see exactly if what we do with the FBDs gives us the exact same thing that we measure in reality. We would find exactly the same thing. Well, remember what we talked about for frames. Our process was to identify, basically, we have our steps here for our frames. And step 1, I'm gonna simplify this down a little bit. We talked about a few more steps last time, but one is to ID all the rigid objects and their type. And so the type just means, is it a 2-force member or is it a multi-force member? So that's what we're talking about there. All those rigid objects give us possible FBDs. And so we then, our step 2 is just to pick an FBD from those options with knowns. It's got to have knowns on there and not too many unknowns. And how many is too many unknowns? If we are in 2D, we typically have 3 equations, sum of force in the X, sum of force in the Y, and sum of moments. And so that sets the number of unknowns that we can solve for. So in this problem over here, oh, and I just noticed that we didn't label the points here. This was point A. This right here is point B, point C, and point D on there. And so that'll help us to identify those objects. Well, what kind of rigid object, let me go to somebody in the front row here. What kind of rigid object is ABC? Max, I saw it's Maxwell, and you're gonna have to tell me how to pronounce the last name again. It starts with an NW. What kind of rigid object is ABC? I saw Max in here. I saw his picture. Okay, let me go up the list then. How about Spencer? Spencer, I know is here. What kind of object is ABC? Is it a 2-force or is it multi-force?
It's 2-force?
No, it's actually a multi-force.
Is it multi-force because of the pulleys?
Well, because of the number of locations. All we're doing is counting the number of locations with forces. And so that's a multi-force. And then we have C to D. That also has more than 2 locations. It has point D right here where the rope connects in to that one right there. And if we look back at the original picture, it probably looks a little bit better, easier to see, right? We have point D where the rope connects in, and up here, there's 3 locations. So they're both multi-force rigid objects. And so those are 2 viable options for us. We can do an FBD at ABC. We could do an FBD of C to D. We also talked about in that video that we could do an FBD of the whole thing. And so the whole thing is always another option for us. So the FBD of the whole, always consider for our problems, okay? So always look at that FBD of the whole thing. And actually there's a couple of different places to start with this one. I'm gonna go ahead and I'm gonna start with the FBD of ABC. And I'm gonna do that for a couple of different reasons here. And when I draw this FBD, we'll talk about why. So I have this FBD of, I have ABC right there. And I'm going to show it kind of big like that with some dimension in the y direction. I've got a hole right there for the pin back there at A. I've got a hole right here where that pulley was located. And then I've got a hole over here where actually we have the pulley and the connection with our other rigid object right there. Well, let's take care of the pulleys first. We talked about in that video that the pulley here at B is going to exert a force going this way on there, and there's going to be another force going this way. So this is a 490.5 newtons. This one right here, also 490.5 newtons. And then at this pulley right here, we're going to have a 490.5 going back to the left and another 490.5 going straight down. So we have, let me see, where can I put these, all these 490.5s so that we can, how about we just say this is 490.5, that's 490.5. They're all 490.5s, right? So all of those are 490.5s. And that's what we're doing is we're transferring the force off of the pulley. We're taking the pulley off, but we know there was a force that the pulley was exerting onto that rigid object. We could actually leave the pulleys on there. That would be another option, is to leave those pulleys on there. And we can look at that option in a second here. So, okay, now what's going on at A? If we remove the pin there at A, we're going to replace that with an AX and also an AY, because that's a pin support. And so that's going to have an X and a Y component. Now at point C, we are also going to have the forces. We removed the rigid object D to C. So we're also going to have a CX and a CY. And I'm just arbitrarily picking what direction they're going in. And it's a CX and a CY because C to D is a multi-force object. So let's label these forces up here, this CX and that CY. These are the forces from D to C onto ABC. And remember that D to C is multi-force. So that's why we have a CX and a CY. If a DC was a two force, we would make it an FC to D. It would be a one unknown magnitude with a known line of action. Okay, let's add our dimensions here. This is a distance of 0.8 meters. This is a distance here of 0.8 meters as well. And that's all the geometry that we really need to add on there. Okay, now let's look at why did I draw this FBD first as compared to the other options. The reason that this one is going to work, really two things. What are we looking for in this problem? We are specifically asked to find the forces at C. So if I want to find forces at C, I need to expose those forces. So that's why that's one of the reasons why I picked this FBD. The other reason is because points A and C, even though we have four unknowns, they're all in this horizontal line. And so I can start to solve for stuff because if I sum moments at A, I can find CY. And so I'm already starting to find some of the forces that I'm looking for in this problem. Now, we can compare that to the other options. And you know, there's nothing wrong when you're going through these problems, nothing wrong at all, absolutely, with thinking about, okay, FBD to the whole, what would that give me? Well, let's go through that here. I'm just gonna go, you know, maybe don't write this down. I'm gonna go faster than I think you can write it down. If I did the FBD to the whole, I would expose AX and AY. I would expose a DX and a DY. I could sum moments about D and I could solve for AX. That's an option. That's a total viable option. If I did the FBD of this one, however, I would have four unknowns. So I'd have a CX and a CY up here, a DX and a DY down here. but they're not in a vertical or a horizontal line. And so I'm not going to be able to solve for any of those, but nothing wrong at all. As we're learning this stuff, and I would actually recommend it, is to just identify all the FBDs and then go through them and say, okay, which one is going to be, really just a process of elimination. Let me try this one. How can I solve for anything? And then, okay, I can or I can't, and then go on to the next one. That's all that, the main thing is that we can identify all the FBDs and that we can draw them correctly and figure out then from that list which one we want to start with. Just like picking a college, right? Like you identify all the options and you apply and you get your financial aid package, and then you start, right? You identify all the options and then you start looking at all the details of which one you're actually going to go with. Okay, so in this FBD here, we can sum moments about A, and we will be able to solve for CY, which is something that we are looking for. So we're going to have a minus 490.5 newtons. That's this first one here, times 0.8 meters. We're going to have another minus 490.5 newtons times the second one. That's a 1.6 meters out there. And then we are going to have a positive CY times 1.6 meters as well, equal to 0 then. And so we are going to find that our CY, the way that I drew the CY there, we're actually going to find a positive number. And we find CY as positive 735.75 newtons. So we actually, since we got a positive number, what that tells us, it means that it goes in the same direction as we drew it. So same direction as drawn on there. Okay, so it's actually a distance of 1.6, and that 1.6 distance, I'm looking at the chat here, that 1.6 distance is the 0.8 plus the 0.8. Okay. Okay, so we found CY. Now we could certainly find AY, but we're not asked to find anything at A. So let's move on to the next FBD. And the next FBD we're going to look at here is an FBD of D to C. And so if the reason I'm looking at D to C is because we know CY and I want to be able to find CX, right? That's what we're looking for. They're asking us specifically to find the stuff going on at point C. So we talked last time, and it was a long, long time ago, right? It was like a week and a half ago, we talked about this. When we have this CX and CY over here on our FBD of ABC, and we said, okay, well, we drew CY going up. Well, we found CY is positive, and so it is going up on this FBD. But remember, those are the forces from D to C on ABC. Over here, what direction should I draw CY? I know CY is going to be in the vertical direction. Should I draw CY up or should I draw CY down? How about Kristen Mazrin?
Would it be up?
Well, I drew it up on the other one, right? And so if I draw it up on that other one, I'm really thinking about now, what is that force doing? So I have this one right here, and then I drew it up on this one. But if this member here is pushing up on this one, then what is this member here feeling?
It would be down.
It would be feeling a downward force, wouldn't it? Yes. So we are going to draw this one going down, so the opposite direction. So our CY, we do know it's 735.75 newtons. And then CX also needs to go in the opposite direction. So when we're looking at rigid objects on the opposite sides of connections, we need to make sure those forces go in the opposite directions, because these right here, these are now the forces from ABC onto D to C. Okay, now down here at D, we have not drawn the dx and the dy anywhere else, so we can pick any direction we want to. I'm going to draw dx to the right and dy up. So remember, when you're drawing it for the first time, we can draw any direction we want to. But then when you're drawing those same forces for the second time, you got to look back and see what you did on any previous FBDs. Okay. Now, this rigid object, I'm going to scroll back to the original picture here. It also has a cable, this cable attached to it. And we talked about this cable has a tension of 490.5 newtons. And it's also important that we look regarding the geometry, where does that fall? Oh, that falls not at 0.8, but it actually at 0.7 meters, because the radius of the pulleys is given as 100 millimeters. So we have this cable right here, and we know the tension is 490.5 newtons, and that is at a distance from point D or A. That's at a distance of 0.7 meters. And then this next one, that would be 0.9 meters, because we have to, this is still, that whole distance from here to here is still 1.6 meters, right? Same as the 1.6 meters in the FBD of ABC up there. And then they also told us in the original problem statement that the height of this thing is equal to 1.2 meters. And now I'm wondering, did we draw all those dimensions? Okay, yeah, we did draw all those dimensions on our original picture there, right? So yeah, A to D is that 1.2 meters. Okay, now, again, the reason why I picked the FBD of D to C, I really, after drawing the FBD of ABC, I had two options. I could have drawn the FBD of the whole. I didn't look at that one because it doesn't expose what we're trying to find, which is the stuff at point C. This one now has three unknowns. And so we can solve for those three unknowns for this problem here. In fact, we only need one equation in order to do this. We just can sum the moments about point D, and we will find CX. So our sum of the moments about point D, let's see, we're going to have a positive 490.5 times 0.7 meters. We will have a minus 735.75 times 1.6 meters. And we will have a positive CX times 1.2 meters. So there's everything that's causing a moment about D. We need to set that equal to 0. And we can solve, and we're going to find that CX is equal to a 694, a positive number, 694.88 newtons. Now, we're not actually done yet. These are not the forces at C acting on ABC. And I want to talk about two key things that are going on here. One of them is that I only put my 490s from the pulley on ABC. What happened to my 490s over here on D to C? I didn't put them on there. I've already accounted for those 490.5s at point C. If I put them on both FBDs, I'm double counting those forces. So we only put it on one FBD or the other. We can actually choose which one we want to put them on. In this case, I put them on ABC because I needed those known values there. Also, if you have two pulleys, and it's not a good idea. It's okay, but it's not a good idea to break up the forces from the pulleys and you have two pulleys, they're both connected to ABC, so I'm going to leave them on ABC. If I have one pulley, then I can really choose either one. But since both pulleys are on ABC, That's another reason that I put them on A, B, C, right? I only have, I've got one pulley that's connected between both of them, but both pulleys are connected to A, B, C. So that's why I put them on A, B, C right there. Okay, so we only put the 490.5s in that one spot. Now, our one more step though, and the reason we have one more step is because they ask for the forces at C on A, B, C, and C, D. This is different when they say find the reaction at C. Find the reaction forces at C. They're specifically asking for the forces at C on ABC, and I'll show you where that shows up in the homework as well. So we have this one more step because of the way they specifically, I'll go back, on member ABC, right? And on C to D. And so because of the way that they worded that, we have this one more step, and that's to take a close-up view at C on both of these members. So like, how about on ABC? There's just a close-up view at point C, right? This is member ABC. Well, what do we have going on there? Well, I have a 490.5 going down here. I've got a 490.5 here. We know we have a CX from our original FBD was going to the right, which we now know is 694.88. We have a CY that's going up of 735.75 newtons. And so the net forces are in like the X direction. Aren't the net forces minus 490.5 plus 694.88? And so it's really, we have a net force at that spot of 204.38. In the Y direction, we have a 735.75 minus a 490.5, and we get a value here of 245.25. In the X direction, then we have a force going this way, and the Y direction, we have a force going up. So these are the forces at C on ABC when we look at those net forces on there. So that's the final answer that they are asking us to find here, is they want us to find those numbers, not the 735 and not the 694.88. Although wouldn't those be the net forces at point C acting on D to C? Because from our FBD of D to C, it's only the 735 and the CX that are acting at point D. So the net forces on D to C would be, let's take a close-up view. Let's look at now, how about our D to C? Well, D to C, the only thing we have acting there is a 694.88 going this way and a 735.75 newtons going down. So these are the net forces. At C on D to C. Any questions? So, you know, these frames and machines can be, we have more going on, but if we break them down into the rigid objects, if we can identify the rigid objects, then we can identify all of our potential FBDs. And then once we identify all of our potential FBDs, we just need to be able to look at each FBD and say, okay, what are the forces that are going to be on this FBD? Both known and unknown. And then just go through each FBD and look at those. Now we can do it intelligently, and we'll start to talk about that, how we do it more intelligently, where we can eliminate things. And one of the biggest ways we do that is just by looking at those ones that don't have any knowns. If they don't have a known, we don't have to look at it because there's no known value, right? They have to have a known value. And so we can just start going through all of our options and saying, okay, will this one work? Will this one work? I mentioned before that we could have done the FBD of ABC with pulleys. Let's draw the FBD of ABC with those pulleys. So what if I had my element ABC and I left the pulley there and I left the pulley there? And then we have our, what are we gonna have here? We have the rope that, actually I'm not cutting through the rope now. I'm not removing the pulleys. I'm gonna leave those on there. And so this is these are all of our physical objects in that FBD. Now at A, we'll still have an AX and an AY. At C, we're still gonna have a CY and a CX, but we're only gonna have the forces in the pulley here, a 490.5 newtons there and a 490.5 newtons there. This, and actually let me do that in a different color. This is internal. Those would be internal forces. And that, so actually that 490.5, but remember what happened to the 490.5s when we took it off the pulleys? Those canceled out. They were both going towards one another, weren't they? Now, another thing that happened though is that this distance right here is now 0.7 meters, and the distance all the way out to here is now 1.7 meters because of that pulley, because to here is 1.6. So like all the way to there, that is 1.6. Our process would actually be exactly the same. We would sum moments about A equal to 0, and we would find exactly the same thing, because this 490.5 is 0.1 meters shorter. So this one right here is 0.1 meters closer to A, but then this one over here is 0.1 meter further from A. So our CY is still going to end up 735.75 newtons. We get exactly the same thing. So we can leave them on the pulleys. We can take them off the pulleys. I tend to like to just transfer the forces from the pulleys onto the rigid object, but either one of those will work. To demonstrate those internal forces, I've got another video here. Let's take a look at a demo for internal forces and how those internal forces work. I have a system here. I'm just hanging this board from the ceiling, and then I've got a frictionless pulley right here at this spot and a suspended mass that's going over that frictionless pulley, and then I have this rope that's attached to just a screw right back here. Now, my support ropes right here and also right here are mostly hanging vertical, even though we know that right here there's this pulley there's a horizontal force acting on this board, right? This pulley, if we transfer the forces from this pulley onto this board, there would be a force going down and there would be a force going back to the right. Well, there's also a force right here acting on this board going back to the left. And so if we drew an FVD of this thing and we cut through this and we cut through this and we included the mass there, then we would not have any horizontal forces because those horizontal forces would be internal. Now, if I take this off of the board, let's say this is connected, this rope here is connected maybe over to the wall, or really it's connected to my hand right now. Look at the support strings. They are now angled, and because that board, the external force acting on that board is a horizontal force going off to the right. I put it back on there, on that screw right there, and now we see those support strings hang vertical again. And so that gives us an idea of how these internal forces. Do you notice that guy's wearing my same shirt? That is like too weird. I can't believe that guy's doing that. Like, he like must have gone into my closet and like stole my shirt or something. Actually, I did not even plan that today. I just noticed that I'm wearing the same shirt in that video. Okay, so it was a little bit more on right, internal forces. And so if we don't cut through it, if we don't have to cut it to separate it from the rest of the world, then it stays internal. In this one, we could have cut through it. We could say, oh, you know what? I'm going to cut through it here and here. And I cut through my string. Well, that means I'd have a force there and I'd have a force there. Look at what happens. They cancel each other out, right? They're internal. They're going in opposite directions. Okay. Any questions about any of that? Or are we having issues with the audio? Let me know if you're having any issues. Yeah, with like the screen is blurry or anything. In my reinforced concrete design class,